All right, so let's try to lock in here for a minute. Um, so what I will say, we're going to be talking about in chapter 15, exponential, logarithmic, and logistic functions. Now, my understanding is most of us that came from the regular algebra class did not see any of this yet. Now, if you came from the honors class, maybe you've seen this already, which is fine. This tends to be conceptually kind of difficult for students. So I'm warning you, especially if this is your first time seeing this, that this tends to be a difficult topic. So I just want to front load that with you to kind of keep it in mind. I'm going to go slow through this and approach it as if you're seeing this for the first time, since many of us are. The last two chapters are things that I know that you did in Algebra 2, so I've been a little briefer with some of the explanations and gone a little bit faster maybe than, certainly than I would have if it was doing it fresh for the first time. But that's kind of what we're doing and where we're going to be at. So we're going to start by just defining what we mean by an exponential function. An exponential function is something of the form y equals a times b to the x. The a is just like a coefficient. Sometimes we call it the initial value. And we're going to make the assumption that a is never 0. Because if a was 0, 0 times anything is 0. So this would just be like a constant function, not an exponential function. That's why we're eliminating a, or the opportunity for a to be 0. B we call the base. That's the piece with the variable attached to it in the exponent. That's pretty embarrassing, man. For the values for B, we're going to assume that B has to be positive and not equal to 1. So remember, if B is equal to 1, that'd just be like 1 to the x, 1 to any power is just 1, right? So 1 times a would just be a. That's a constant function. Again, we don't want that. That's why we're throwing out the possibility for b to be 1. We also don't want b to be negative, because remember, if x is a variable, that means x could be like things like a half or a fourth or a sixth. Those represent even roots, right? Like square roots or fourth roots or sixth roots. And we can't take the fourth root or square root or sixth root of negative numbers. So if we did allow b to be negative, this thing would be undefined all over the place, which would be like a really disgusting function that has like infinitely many discontinuities, and that's just like a mess. So that's why we're not allowing b to be negative either. And then the x we just call the exponent. Okay. Every exponential function of the form y equals a times b to the x has a key feature. They all have horizontal asymptotes at y equals 0. And depending on the value of B, that means the end behavior is either going to be that. So you have either one of these sets of end behaviors. Essentially what we're talking about is, the graph will either look like this, or it could look like this. Or the graph might look like so just by looking at the values for A and B, we can identify what the graph is going to look like, or the basic shape of it. And from that, we can identify the end behaviors, right? One end behavior is going to always go to the horizontal asymptote, and the other is going to go to positive or negative infinity. And the values for A and B will tell us which is which. So far, so good? Okay. What I want to do next is just kind of remind you guys about some exponent rules. So if I have two exponential numbers where the base is the same, I can multiply them together by adding the exponents and keeping the base the same. Or if I have two exponential numbers that have the same exponent, I can multiply them together by multiplying the bases together and keeping the exponent the same. Those are the only two ways that you can multiply exponential numbers. So for example, if I have like 2 to the third times 2 to the fifth, that's just going to be 2 to the eighth. Or if I have 2 to the third times 5 to the third, that's going to be 10 to the third. What you're never able to do is if I have 5 to the second times 10 to, or 2 to the third, I can't do anything with that. Okay. Notice that the bases for the two exponentials are different. One is 5 and the other is 2. And the exponents are different. One is 2 and the other is 3. So there's nothing to do there. Can't do anything with that. Because the place where students tend to make a bunch of mistakes is if we have the exponential function -2 times 4 to the x. What I see students frequently do, especially that are new to this idea, is call that -8 to the x. Do not do that. There's no recovery from that. I will earn you 0 points of partial credit if you do this. Okay? It is a number one, big time no-no. Do you guys see why? Because the -2, the base is a 2 and the exponent's a 1. The 4, the base is a 4 and then the exponent's an x. They're both different, so you definitely can't multiply those two things together. Yeah? Okay. What I want to do here to practice some additional exponent rules is just to evaluate this function f at some different values of x. So if this says f of 2, all it means is that I just need to plug 2 in for x, right? And my order of operation says I should do exponents first, so that 4 squared is 16. And then -2 times 16 is just -32, right? If I do f to the 0, I'm just going to plug 0 in for x. So I have -2 times 4 to the 0. What's 4 to the 0 equal? Not 0. 1. So remember that our exponent property says that any number other than 0 to the 0 power is equal to 1. Zero to the 0 is undefined, just FYI. Actually, it's worse than undefined. It's all called indeterminate. But that's beyond the scope of this course. You can think of it as undefined. If I plug -3 in, I'd have 2 times 4 to the -3rd. What does a negative exponent mean? It's like a reciprocal, right? We flip it. So that would be -2 times 4, or 1 over 4 to the 3rd. 4 to the 3rd is 64. So I can like do a little reducey-ruski on that. So again, the exponent rule that I used there was like, I guess we'll just use x's. Everybody okay there? If I do f of 1/2, again, I'm just plugging the 1/2 into x. So -2 times 4 to the 1/2. What does a 1/2 exponent mean? Square root. Very good. So remember all of our unit exponents, like 1 over number. The number tells you the index of the radical. And that's nice because the square root of 4 is just 2. So again, our rule we used there was like x to the 1 over n is just the nth root of x. And remember, when n is 2, that's like the square root. We usually don't write the 2 in the index. It's not wrong if you do, but just like we don't write powers of 1 or coefficients of 1, we don't write an index of 2. And then our last one is going to be this, right? Negative 2 times 4 to the negative 3 halves. Everybody's okay there? And then just like before, I'm going to do my negative exponent property to give me 4 to the 3 halves, or I'm sorry, 1 over 4 to the 3 halves. So far, so good. But how do I do 4 to the 3 halves there? So what I want to do is I want to think about it as like 3 halves as 3 times 1/2. Because I remember there's a property for exponents. That if I have a power, we multiply those exponents. So I'm just going to use this property to kind of go in reverse. Now, before we do that, let's think about it, because I could have written it as 1/2 times 3 instead of 3 times 1/2, correct? Which one of those is going to be the better choice, do you think? They're both correct, but one of them will make my life a little bit easier. Yeah, dead on. So let's do that one. So that's 4 to the 1/2 to the 3rd. And I like that because I know that 1/2 is the same thing as a square root. So it's just going to turn into like 2 to the 3rd. You guys good there? And then I can do my like reducing property. Or really, I would probably just think about it this way. How do you feel so far? So basically, I just wanted to do some of these problems to review some of our properties of exponents, because it's been a little while since we've probably done anything with them. It's easy to kind of get turned around and confused and misremember stuff. Yes, sure. All right. Next idea is, what if I wanted to take a table of values and convert this into an exponential function? Now this should look like a familiar problem because we actually did this already in chapter 11 when we did our modeling, right? Where you just kind of type your table into the calculator and use the exponential regression or whatever. I'm also going to show you how to do this by hand in this chapter under certain circumstances. So if our table of values, if one of the points in there has the x value of 0, very easy to do this by hand, but we have to have that x value of 0 to do that. Sure. So what I want is I want to write down a exponential equation. So I'm going to start by using that 0.03 and plug that into my x's and y's. The reason why I want 0 is because I know b to the 0 is just 1, right? B to the 0 is 1. So I'm just left then with a equals 3. Everybody feel okay there? So now I can choose, now that I know A, I can choose any other point to plug in and find B. Which point is going to be the easiest one to choose? Well, I want the one where my exponent is closest to 1 as possible. Like, don't make life harder than it needs to be. So if I just divide both sides by 3, I get that b is 5. So if I put those guys together, I can just say this is y equals 3 times 5 to the x. Can I say it's just equal to 15 to the x? No! We just covered it. Because you can't multiply exponential numbers that have different bases and different exponents. Right? So I have 3 to the first and 5 to the x. The bases are different, so you can't add the exponents. And the exponents are different, so you can't multiply the bases. So there's nothing to do on that. Okay. The other situation where I could give you points and ask you to write the equation would be if I give you just 2 points. And now these two situations that we've gone through where I give you a table but the x value of 0 is included, or if I give you just 2 points, these are the only two situations you'll have to write an equation from a table. So again, the idea here is I want to write an equation a times b to the x. So what I'm going to do is I'm going to take one of my points and plug them in for x and y. And I'll do it for the other point as well. So I'll do it for both points. And what I've created is a system of 2 equations. Now, last year in your algebra course, you would have probably spent a whole chapter solving systems of equations. You did things like substitution and elimination and graphing and maybe used a matrix and who knows, some other techniques. But always in those situations, your variables were added together, right? You had like ax or like 5x plus 3y equals 10, and then like 7x plus 10y equals 9, and you're solving a system like that where the variables were being added or subtracted. Here they're being multiplied, right? So the technique to do the elimination, which is the method we're going to use, is a little bit different. Because the variables are being multiplied, I have a times b. To do elimination, I need to do division. So I'm either going to take equation a and divide it by equation b, or take equation b and divide it by equation a. It doesn't really matter, but we can make our lives a little easier on ourselves by making a careful choice here. So the numerator of my division problem, I want to choose the equation where the power of b is the bigger power. So -1 is bigger than -3. So I want to do equation b divided by equation A. So to do that, I'm going to divide the left-hand sides. So 12 divided by 48 equals, and then I'm going to divide the right-hand side. So A times b to the negative 1 divided by A times b to the negative 3. Well, 12 over 48, I can just reduce that fraction, right? That reduces down to 1/4. A times b to the negative 1 divided by A times b to the negative 3. Well, the a's can cancel. And I'm just left with b to the negative 1 divided by b to the negative 3. And I know from my rules of exponents that we just talked about that I can divide those by just subtracting the denominator's exponent from the numerator's exponent. What's negative 1 minus a negative 3?
Negative 2.
Just positive 2, right? Negative 4. Great googly moogly.
I thought you just said negative 1 minus 3.
Negative 1 minus a negative 3?
Oh, no, I thought you just said negative 1 minus 3.
Okay.
I didn't see the minus and the negative, no. Just never mind.
Okay. So now we're at b squared equals 1/4. That we can solve though, right? We'll just square root both sides. Now when I square root both sides, I get a plus or minus. How do I square root a fraction though? Great, we square root the top and the bottom. Right? That's a rule. Yep. So the square root of 1 is 1. Square root of 4 is 2. So it's just 1/2. And we can do even a little bit better than that. Because remember what our definition for an exponential function was way back in the beginning. We said that value for b has to be positive. So guess what that allows me to do? Get rid of the negative from the plus or minus. Sweet. So now that I have that b is equal to 1/2, I can plug that back into either equation A or B. I'm going to choose to plug it into equation B because the exponent in equation B is closer to 0. So I don't necessarily want the biggest exponent here to make this easier. I want the one closest to 0. So I'm going to have 12 is equal to A times 1/2 to the negative 1. And what does that negative exponent again do? Makes a reciprocal. So the reciprocal of 1/2 is just 2, right? So if I divide by 2, I get A is 6. So if I take those together, I'm going to have y equals 6 times 1/2 to the x. Notice that I put a parenthesis around the fraction here. That is standard practice, that you put a parenthesis around a fraction if there's a exponent involved, because we don't want to be confused with like 1 to the x over 2 is not the same as 1 over 2 to the, 1/2 to the x, because this is equal to 1 to the x over 2 to the x, right? So I am going to be a stickler about seeing that parenthesis there. If you don't include it, I'm going to mark off. All right. Now, there is a special value for b. That special value, go ahead. That special value for b is this irrational number 2.78128, yada, yada, yada. So that's a number that we can't write as a fraction. It never terminates, goes on forever. There's no repeating pattern to it. It's kind of like the number pi, where we give it a special name. We're going to call it E. This is named in honor of the mathematician Leonard Euler. It's like a 17th century or...
Did he also make the order test?
What?
Did he also make the order test?
Mm-hmm. Yeah, he's very important mathematician, did a lot in like algebra and algebraic geometry. Probably you're like the best mathematician of his kind of generation. So it's named in his honor. And the reason this is important value is that every exponential function of the form a times b to the x can be written as y equals a times e to the kx. Now, you might be wondering why, who gives a rip? Like, why does it matter? Like, it looks like the same thing. Well, if your exponential functions, if you're trying to compare two of them and they have different bases, it's really difficult to get a good idea of like which one is, like, how are they growing? What is the difference between one to another? If you can write them with the same base, though, it's much easier to compare the two functions. So that's the value here, is that we're able, it's like our universal translator, is I can take any function or any exponential function and I'll write them all with the same base. And a little bit later into this chapter, we'll kind of show you where this number kind of comes from. But that's enough for right now on that. And the last thing I want to talk about are the types of exponential functions. So we have two types. We have growth and we have decay. So a function with exponential growth is, as we move from left to right, should be increasing. So it could look like that. Or it could look like that. A function with exponential decay should be decreasing as we move from left to right. So it would look like one of those two. So we can identify whether it's growth or decay just by looking at the coefficients or the values for A and B, or A and K, depending on which form we've written our function in. So my exponential growth that matches the red graph is going to be A positive and B values greater than 1. If it's the green graph, the A is going to be negative and the B would be between 0 and 1. Or if it was written in the form with E in it, we would have A positive and then K positive, or A negative and then K negative. Hi, Mr. Cater, what's up? I
I don't know how you know that, first of all. That scares me. Math scares me. Sorry to interrupt, but can I borrow Mr. Sink?
He just went to the bathroom.
Okay. All right.
Should I send him to go look for you?
No, wait for him.
Okay. You get to hear some more math then.
Oh boy.
Yeah.
30 minutes. Yeah, this is good.
I'm stopping at the end of, I have 4 more things to write and I'm done. So,
You're doing a really nice job.
thank you. All right. So if we're looking at the decays and we're in the form a times b to the x, the red graph is positive a's, but the b's between 0 and 1. And then the green graph would be negative a's, but b's greater than 1. And then if we're in the other form, the red graph is a greater than 0, but k less than 0. And the green graph would be a less than 0, k greater than 0. And this one I should have written in green down here, huh? And this is my stopping point. My apologies for taking 6 minutes and 25 seconds longer than I told you to.
It's okay.
But this is where we'll stop. We still have more to finish up in 15.1. So you could start on the 15 homework at this point. Probably not. You stop when you get to the word problems. If you're so inclined on getting a head start on things because you're going to be gone for Kairos next week or something. Sure.
Is there going to be a problem set due on Sunday?
So this Sunday's problem set was just the chapter 14 review. So I think that's the only thing due this Sunday.
Okay.